My name is Mariusz Postal and I am representing the Institute of Information Technology, Łódź University of Technology. It is my pleasure to present my and Piotr Szymczak research work related to object-oriented Internet and cloud services integration. We are proposing a generic architecture that we use to implement and deploy this interoperability scenario. Based on the role humans take while deploying the smart factory concept, the computer applications may be grouped as human-centric or machine-centric. A typical human-centric approach is a web service, supporting a web user interface to monitor conditions and manage millions of devices, and their data, in a typical cloud-based Internet of Things approach. In this case, it is characteristic that any necessity to decide can be relaxed by human interaction. An example of a machine-centric scenario is the coordination of robot behavior, in a work cell. In this case, any human interaction must be recognized as impractical or even impossible. This interconnection scenario requires machine-to-machine communication demanding multi-vendor device integration. In this case, the solution must be robust by design because no human interaction is applicable at runtime. To promote a multi-vendor environment, the standardization is especially important. Industry 4.0 is an idea that addresses the smart factory concept design and deployment. That concept is recognized as the fourth industrial revolution. Additionally, to address interoperability of the multi-vendor parts requirements, the OPC Unified Architecture is considered, to normalize machine-to-machine communication. The main goal of this article is to prove that the cyber-physical network can be interconnected with the Internet of Things cloud services, based on the OPC UA standard, implemented as a powerful standalone library, without dependency on the client-server session-oriented interoperability scenario. In our proposal, cloud interoperability is implemented as an independent part employing out-of-band communication without dependency on the OPC UA implementation. Additionally, the proposed generic architecture allows that the gateway functionality is implemented as a composable part at runtime. No programming is required. To promote reusability, the research must be conducted atop of a formal description. The proposed solution, and all intermediate steps illustrating how to derive the final solution from the selected domain features, are described using the UML. Finally, the workout is abstract enough to be reused in any development environment. On the other hand, we published 2 open-source implementations as proof of concept. Before conducting any further research, we must address the question about the relationship between the cloud-based front-end and cyber-physical network. The first natural option is the presented on the slide: direct interconnection. By design, the direct interconnection approach requires that the cloud has to be compliant with the interoperability standard the cyber-physical system is based on. This approach is not practical, became by design. The cloud-based services require that for interconnection preparation and data interchange is conducted over the Internet. Contrary to this, machine-to-machine communication is usually constrained by real-time requirements to use protocols applicable only to local computer networks, for example multicast IP, Ethernet, TSN, etc. Concluding, it is obvious that, because the cloud services support only communication over the Internet, the direct interconnection cannot be applied in a general case. An edge entity is a remote cloud agent, acting as an intermediary for nodes of the cyber-physical system. It is a consistent part of cloud-based front-end services. The main disadvantage of this solution is the possibility to support interconnection with only one cloud service. Field-level gateway is a dedicated custom agent, acting as an intermediary for nodes connected to the cyber-physical network. This solution is not constrained by the cloud vendor communication context, and, as the result, may be used to handle communication with a variety of clouds. Still, this solution is constrained to fulfill the gateway functionality only. We propose a new architecture, derived from the field-level approach, but not constrained to gateway functionality only. The embedded gateway is only a composed part of the networking services of a cyber-physical node. In this approach, it may be assumed that the gateway functionality is only an add-in to expand the typical functionality of the node, including but not limited to, establishing semantic and security context with the other nodes, connected to the cyber-physical network. The responsibility of the embedded gateway is to establish communication context with the cloud-based front end and conduct the selected data transfer in compliance with the context. Embedded gateway is composable to any cyber-physical node. It is worth stressing that it could be deployed far after designing and deploying the hosting cyber-physical node. The only requirement that constrains this approach is a common abstract contract, usually expressed as an interface, that the embedded gateway must be compliant with, to be aggregated to the whole. In other words, in the proposed solution, the gateway is loosely coupled with the node, contrary to the edge and field level approaches, where the gateway functionality is tightly coupled, say embedded, with the host. It improves flexibility, reusability, and in general, maintenance cost. It is a theory, abstracting a generic solution, meeting community expectations. In other words, it is just a set of assumptions that now we can use to propose a concrete implementation meeting the assumption. I believe that a detailed description of the implementation is not relevant to us, in contrast to an analysis of how to use the proposed domain model to make strategic design decisions and functionality distribution. To meet the project requirements, reusability and flexibility, the following design patterns have been used. Separation of concerns, to allow independent development of the parts. Dependency injection, to allow late binding of independently implemented parts. Adaptive programming is used at the development and deployment stage to improve the adaptability of the program against changes in the production environment. Piece-by-piece integration of a cyber-physical system, using multi-vendor products, requires that machine-to-machine communication employs international standards as the interoperability foundation. OPC Unified Architecture Part 14 Pub Sub is selected in this respect. As I stressed previously, the proposal is backed by proof of concept reference implementations. Prototyping addresses Microsoft Azure Cloud Services as an example. The outcome has been just published on GitHub as the open source repository. The proposed solutions have been harmonized with the more general concept called the Object-Oriented Internet. To start prototyping, we did use a library called UI networking.semantic data. Networking for short. This library offers a generic implementation of the mentioned OPC Unified Architecture Pub Sub standard. It is generic because allows selecting one of the transport protocols allowed by the spec to connect the node to other nodes attached to the common cyber-physical network. Additionally, using a different implementation of the encoding component, many variants of the network message compliant with the spec are configurable and may be aggregated by the library at runtime. Encoding and underling protocol stack are responsible to support in-band machine-to-machine communication. Concluding, these composable parts are responsible to handle cyber-physical network communication. In the proposed solution, process data binding is offered by the data repository, which implements the iBinding factory interface. The producer and consumer roles are derived from it to support bidirectional data exchange with the underlying real process. By design, they support access to real-time process data. Independent implementations of these roles can be composed by the reactive application using the dependency injection programming technique. It follows the separation of concerns programming concept. According to this diagram, our implementation of the consumer role has been used to provide embedded gateway functionality and out-of-band communication with cloud services to transfer data to Azure IoT Central Solution. The most important feature here is that the reactive application uses late binding to compose the custom implementation of the gateway. As I said previously, it allows implementation of this role even after deploying the hosting application. In other words, current consumer implementation is injected part of the reactive application compliant with the OPC UA Pub Sub. Using other implementations of the producer-consumer roles means that a vast variety of functionality can be provided at the same time. Using many consumer implementations it is possible to get connected to any cloud services, using out-of-band communication, compliant with cloud services connectivity requirements. Our prototyping addresses only Azure interoperability as just an example. It is worth stressing that the hosting application of the embedded gateway part, based on the consumer functionality, is a fully functional member of the cyber-physical network. The implementation contains two major components, namely, communication context and part binding factory. Part binding factory is responsible for grouping and processing the data recovered from the messages exchanged over the network. Integrating these two different environments, we must assume that metadata used to describe the data exchanged over the cyber-physical networks and the data exposed by the cloud solution are not compliant. For example, to be compliant with the specification, the cyber-physical data exchange must be described using encoding required by the OPC Unified Architecture spec. On the other hand, the cloud solution metadata may be described using digital tween description language that is not stable. In other words, these two environments use different domain-specific languages to describe the syntax and semantics of the same process data. Therefore, based on the bitstream's meaning, this class of the gateway must be also responsible to provide mapping at runtime. The result of the mapping is converted to data transfer object using JSON serialization. This data transfer object factoring mechanism must be conducted every time new data is to be sent to the cloud, but the behavior of the mapping may be considered as the design time activity in a typical case. Communication context class sends the created data transfer objects using a communication channel established in advance. The data transfer object is retrieved from the part binding factory using the IDTA provider interface. The communication context maintains the data transfer channel with the cloud services, using a well-known state machine pattern. It is responsible for protocol stack selection, authentication, and authorization of a session created to establish a communication channel. The encoded JSON messages must be transferred to the cloud over the network using the selected protocol stack. Azure and PubSub use different security mechanisms, so in the proposed solution establishing security context is realized independently using the configuration. The communication context is responsible for establishing the connectivity and security contexts. Finally, communication context uses out-of-band communication to send data to the cloud services. My point is that this gateway experience may be easily ported to implement OPC UA server and OPC UA client gateway. A next topic that could be a good candidate for further work is a systematic approach to the semantic mapping between different domain-specific languages, namely languages defined by the OPC UA specification, and digital tween description language, that is to be used to define metadata on the Azure services. Additionally, a gateway on the stick should be concerned, namely self-contained application without cyber-physical network interoperability. In this case, data gathered by the producer is sent directly to the cloud, using the consumer role implemented to fulfill the gateway functionality. Thank you very much for your attention. Contact me directly in any case questions or proposals you may have.